it was actually right under this bridge that I discovered what I will choose as my video project this year for my complex structures. In fact, it was this frame right here. I remember it was raining really badly, and I came here on my bicycle just right over there, and I was kind of stuck here for 30 minutes because of the rain, so just staying under here protected me from it. Yeah, anyways, what I'm going to be doing is basically I'll be just doing an explanation about how I've done my video project. I'll be doing a little bit of a different approach. I remember when I did the structure analysis in 2018, I wasn't creative enough. But this time, I think it's going to be a little bit different. Yeah, so we'll go back to my place now, and we'll work out the calculations and see how we turned out with them. Alright, officially reached home. Now I'm gonna go about how I have done the calculations. I'm gonna do something a little bit different because I've noticed a lot of people will probably be using PowerPoint slides. So instead of that, I'm actually gonna go over my calculations, which I did handwritten. Okay, let's do this. Okay, all right, here we go. So yeah, we know that there's we used 4 methods to solve everything: force method, slope deflection method, moment distribution method, and approximate analysis method. Yeah, so the first one we're going to be going through is the force method. So we know that in order to make the calculation easier, we have to remove one value. So we removed dy from here. No, we removed bx from here. Sorry, apologies. So it became primary plus redundant, and this is the assumed deflection profile. Okay, and we basically did all the necessary calculations. We found dy by using the sum of moments about d is equal to 0 formula. Now we found our ay using the sum of forces in the y direction. Okay, and then we found the sum of forces. We found the sum of forces in the x direction, and then we found our ax primary. We got all the answers over there, and now what we learned is we have to assume there's 2 moments and forces, 2 moments acting in there. Yeah, internal moment and external moment. Okay, so external moment is it's capital letter M, so big letter M there, and M there, and then the internal moment is the small letter m, which is here, here, and here. Okay, so we've done all the necessary calculations. Okay, and we have found all the answers. All right, and then after that we have to input everything we have found in this formula. All right, so we input everything in, and then we integrate it. After we integrate it, so basically just I'm gonna do the first one. Actually, this is all combined, I think. Oh yeah, okay, sorry, I forgot, I haven't done this in a while. Okay, and I should not actually forget because I have to study for the exam. Yep, all right. So 79.92 x3 squared minus 3.33 x3 plus negative x1 dx plus 1 over ei into 6.66 x2 cubed minus 139.06 x2 plus negative 12 dx plus 1 over ei is equal to, that is a 0, I think. Yep, 0 x, yep, minus x3 dx3. Okay, we've gone about solving that, input all the values in, and we've come to the final value of, so change in a is equal to 1309.45 over ei. All right, and now our job is to find the FAA. We've done all the necessary calculations once again, and we have come to our value of 1843.2 over ei. Okay, and now we have to find our dx. Now with the dx, we're given a formula to use, and we have used this formula to find the answer. Now remember, we have actually already solved for everything. We just have to find the dx. Okay, so we input everything in the formula, and we have come with our final answer of 0.71 kilonewtons. Okay, and to find the AX, basically sum of forces in the x direction is equal to 0. Input everything in, and you get AX is equal to 79.21 kilonewtons. Okay, and now we will now we will use all the answers given here, go all the way over here, so we can come up with our basically all our forces. Sorry, not all forces. Yeah, forces and our x values and everything that we didn't actually know at the back over here. So for column AB, sum of forces in x direction is equal to 0. Solved everything here. We got our x1 value is equal to 11.89 meters. How we found that is we've actually used this formula right over here. Okay, and now we have found, now we're gonna find the m x1 max. Okay, that's our formula. Negative 3.33 into 11.89 squared plus 79.21 times 11.89. And we get a value of 471.04 kilonewton meter. This 11.89 is from right here, and this 3.33, where did it come from? I think it's just half of this 6.66. I think that's where it came from, and then this 79.21 is our AX. Yep, and then we're doing the same thing for beam BC. We find our sum of forces in the y direction, and then we find our sum of moments C about 0. Go about here, and then we go about finding our D, which is our distance, which is the m distance, internal moment x, which is D is equal to 2.09 meters. We do the same thing for column CD, but the thing with this one is there's like barely any calculations because there's actually no force acting here. So you see a lot of zeros and zeros. So the force at x3 is going to be negative 0.71 kilonewton, and internal moment here is going to be negative 0.1 x3. So that's all done for the force method. And in the slope deflection method, thing with the slope deflection method was that it wasn't actually very difficult, but there was just a lot of formulas. Okay, so one formula for span AD, one formula for span DA, another formula for span DC and CD, and where else is it? One more for CB, one more for BC. So altogether there were actually 10 formulas. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so now we have to solve this, not all of it simultaneously, but we have to solve some of these equations together simultaneously in order to find the answers. Okay, so the first one we're going to use to solve is number 9 and number 10, just right over here. Once we solve it simultaneously, we get our theta C. We get our theta D first. Okay, after we get the theta D, we will find our theta C. Okay, as you can see, the values are very, very similar. It's just there's a negative value here. Okay, and after we found those both answers, see, we're gonna sub it into the rest of the equations. See, equation number 1, equation number 2, 3, 4, 5, and 6. And we have found all our respective answers here. 1, 2, 3, 4, 5. 5 and 6. And after we found all the answers, we will so bending moment diagram, which we have got by solving all of the questions. And now we have to find the shear force diagram. We very quickly solve for frame 1, and then frame 2 right here, and then the third frame. Okay, after we solve that, we have come up to this as our answer for the shear force diagram. Okay, and now what we're going to do is we're going to quickly switch books. I'm going to close this, and I'm going to open up another book for the moment distribution method, which is just right over here. Okay, now the moment distribution method, I actually found it quite interesting to do because it gave me a chance to use Microsoft Excel, which you will see very, very soon. All right, I'm just a little bit tired because I'm standing around and doing this thing. Oh my god. Okay. Yeah, so luckily for us, we were asked only to use the top load. So the top load was 6.66 kilonewton per meter. This value was, I think, unique for everyone. So yeah, and then I put my dimensions there, 12 meters, 4.8 meters, all right? Now, we're supposed to find the moment of inertia for our section. So mine was a hollow section. So, and these are the dimensions. 200 was the outside how do I explain this? Yeah, this was my capital letter B, small letter B, capital letter D, small letter D. Okay, yeah, I hope that made sense. Yeah, I input everything in the equation. All right, here. Got my answer here. Okay, same thing for moment inertia for our beam BC. Okay. Done all the necessary calculations, got our answer, and now our job is to find the distribution factor. Now what we must know is the distribution factor is going to be equal to 1. So what I did was, yes, I used this formula, dFBA is equal to KBA over KBA plus KBC, right? Okay, and yeah, solve this, got the answer right over here, all right? And now I knew that the answer would, and I knew that because it's a distribution factor, the total is going to be equal to 1. So instead of solving for dFBC, I just subtracted it by 1. So 1 minus 0.7084, I got that, 0.2916. And then I found my FEM. I think the long form for FEM is finite element member. I googled it. I'm not really sure, but yeah, it's always good to learn the long forms. Yeah, so that was 0, 0 for AB, BA, CD, and DC. However, for BC, we do have a value. All right, so we use the formula negative WL squared over 12, and we got our answer as 12.78 kilonewton meter. So after this is really, really interesting what I did. Okay, because I used Microsoft Excel as I said I would, and this is just here on my laptop. Okay, now thing about this is this one I input the values here. Can you see that? Okay, I input the values in there and then in here, and then the rest of the things, Excel didn't do it, I made Excel do it. So everything of this has a formula. Everything has been, see, carried on 1, 2, 3, and then we have the distance 1, 2, 3, 4, and then the sum of moments. My sum of moments was absolutely equal, so I knew that my calculations were good. Okay, yeah, so if you click on one, see, you will see that I've it's not that clear, sorry. Okay, there you go. You will see that I have actually done the necessary equations in Excel. So what I have done is in the appendix I've actually attached this original Excel, so if you want you can go have a look. And I've also attached the answers, which I will open up. Where is it? Here. So I'll put it up on the big screen. I've got this little big screen to study. There's the link right there, moment distribution method, and the answers are actually here. It was actually really interesting to do, as I said, because I used Microsoft Excel. It was really, really fun. Yeah, I got a thorough understanding of it. And the next one is obviously the approximate analysis, which was obviously, it was actually quite a pain to do. Actually, the approximate method for top loading was very simple. That's the value there, everything there, and then I got my answer. It was very simple. I just used my bending moment diagram, the previous one, and I got the answer. Okay. And then this one was the really tough one, horizontal UDL on the left side of load. Divided in the middle, I divided it by 2. Okay, and that gave rise to EY, EX, EY, EX. Did the necessary calculation for the moments,
because we need to find the EY/EX in order to go ahead with our solving of the question. Okay, so we got our equations here, and we did simultaneous equation. I got EY as 99.9 kilonewton, and I got EX as 19.98 kilonewton. It's got the little K there. Sorry about that. That was a little bit of a mistake. I put everything in the equation. Okay, after I did, and now it was time to solve for sum of forces on the X direction, which I did. Okay, over there, and then the sum of moments in at X value, so X3. Just over here. Okay, so I did that. I did the same thing for Vx1 and Mx1, and yeah. After that, what we did was we found the local max. So this is the distance where you'll have the maximum bending, 2.09 meters. Okay, and local max maximum bending moment will be a value of 96.21 kilonewton meter. All right, and then after doing all the necessary calculations, we got our shear force diagram here, and we got our bending moment diagram here, and that wraps it. That was awesome.
Yeah, that was it. I hope you enjoyed that. Now, as we are reaching the end of the video, what I just wanted to say is it was enjoyable learning from you, Shri, this semester, and I hope, well, I don't know if you'll probably teach me again, because I am graduating next year, but I just want to say it's been an honor. Thank you very much. I know it must have been really tedious for you looking at all the calculations of, I don't know, about 200 students, so I've made like a nice little time lapse, which I think you might enjoy. It's less than 2 minutes long. I hope you enjoyed.
I know that this video has been a little bit longer, but the thing is, I wanted to make this video unique. I didn't want to make it just very generic. I enjoy making videos. I recently started making videos, and I thought, oh, this is gonna be a good opportunity for me to do what I really like. So I hopefully you've enjoyed the video.